Hello everyone, I'm Xiuling Wang, a PhD student from Stevens Institute of Technology at New Jersey, US. I'm going to present our work titled Providing Item-Side Individual Fairness for Deep Recommender Systems. This is a joint work with my advisor, Wendy Wang from Stevens. This work is funded by National Science Foundation. Although recommender systems have been demonstrated as efficient and effective, the issue of fairness in these recommender systems has raised serious concerns. Fairness in recommender systems can be classified to two categories: user-side fairness and item-side fairness. User-side fairness requires that users should be treated equally by the recommender systems, regardless of their demographic, property, or their activeness on the recommender system platform. While item-side fairness requires that items should receive equitable exposure by the recommendations, regardless of their popularity. Item-side fairness can be further divided into group fairness and individual fairness. Group fairness requires that items in popular and unpopular groups should be treated statistically similarly, while individual fairness requires that similar individual fairness should be treated similarly by the recommender system. In this paper, we mainly focus on individual fairness at item side in the recommender system. We have the following contributions. First, we formally define alphabet fairness as our individual fairness notion. At a high level, alphabet fairness requires that any two similar items whose distance between their embeddings are less or equal than alpha must receive similar coverage. In other words, the difference in their recommendation coverage should be less or equal than beta. Second, we designed two bias mitigation methods. One algorithm named embedding-based ranking, abbreviated as ER, is an in-processing method that takes user and item embeddings as input and learns a ranking policy for recommendation with alphabet fairness as a constraint. The other algorithm, named greedy substitution, abbreviated as GS, is a post-processing method that takes the original biased recommendations as the input and replaces the item of higher coverage in the recommendations with similar ones but of lower coverage to achieve alphabet fairness. Third, our experiment demonstrated that both ER and GS methods can address the trade-off between fairness and accuracy of recommendations. Furthermore, ER outperforms both GS and the existing solution in terms of the trade-off between fairness and the recommendation accuracy. Next, I will explain the details of our fairness definition. Alphabet fairness. A recommendation algorithm provides alphabet individual item fairness if and only if for all items that their distance are less or equal than alpha, they must satisfy that their coverage disparity are less or equal than beta, where alpha beta are user-specified thresholds. We measure the distance between two items as the cosine similarity between their embeddings. We say if the items are alpha similar, then their embedding distance are less or equal than alpha. We measure the item coverage disparity between item R1 and R2 as the distance between the normalized item coverage of these two items in the recommendation list. Next, I will introduce our bias mitigation algorithms. The goal of ER-based ranking is that with the user and item embedding of the original graph as input, ER finds an optimal ranking policy that maximizes the recommendation accuracy of pi over all users with alphabet fairness constraint. The objective of ER method is defined in equation 1. The ACC part quantifies recommendation quality, which can be calculated with DCG and DCG average ranking, etc. The B part is to quantify the violation of fairness, namely the coverage disparity of the ranking for all users in U, which is formalized by the equation 2. The E algorithm is illustrated in the figure. First, we initialize the model parameters with the embeddings from the original recommender system. Second, with these embeddings, we calculate user item probability following the architecture of the neural collaborative filtering model. Third, we apply Monte Carlo sampling of all possible permutations for each user and calculate the probability distribution for each permutation by using the Plackett-Luce model. Fourth, we compute the gradient for recommendation accuracy and fairness respectively. Finally, we update by using the SGD. We repeated these steps until we reach the convergence. The termination condition is that the accuracy improves less than 1% compared with the last iteration for 5 continuous iterations. The goal of GS is to substitute the high coverage items in the recommendations with low coverage items while maximizing the recommendation accuracy. The objective of GS is defined in question 3. It maximizes the utility of recommendation subject to alphabet fairness constraint. The utility is calculated as the total user item preference scores for all users, which is generated by the original recommendation algorithms. Then the problem can be reformulated as equation 4, which is to minimize the difference between recommendations utility before and after substitution. This algorithm has 3 steps. Step 1, to speed up the search for similar items during replacement, the GS algorithm partitions all items into a number of clusters so that the items in each cluster are pairwisely similar. Second, the algorithm picks items for replacement to meet bit coverage disparity for each cluster. The basic idea is to replace items of high coverage with items in the same cluster of low coverage. One challenge for realizing this strategy is to determine whether an item is of high or low coverage. To address this challenge, we calculate the lower and upper bound of item coverage of all items in the cluster that is guaranteed to make the whole cluster achieve alphabet individual fairness. Step 3, the algorithm replaces the item and updates the coverage. Then repeat step 2 and step 3 until items in each cluster achieve alphabet individual item fairness. We have performed an extensive set of experiments. Here are summarized the main observations from our experiments. More details can be found in the paper. We use cell phone and beauty dataset in Amazon e-commercial dataset. The table below shows the statistical of 2 datasets. For 2 datasets, we have different alphabet settings. 3 alpha values are determined by controlling the percentage of item pairs evaluated as similar on each dataset. They lead to 0.1%, 0.5%, and 1% of such similar item pairs, respectively. We use 3 state-of-the-art deep learning-based recommender systems, CKE, PGPR, and KGAT. These are popularly used by the research community. We use normalized discounted cumulative gain, NDCG, precision and recall of the top 10 recommendations to measure the recommendation performance. We consider 2 baselines. One is named minimum coverage, abbreviated as MC. MC involves minimum item coverage requirement on all items in the recommendations. In particular, given original bias recommendations and an item coverage threshold, we randomly select an item whose coverage is below the threshold and replace it with the item that is of the high coverage that has not been replaced yet. We replace the substitution until the coverage of all items is above the threshold. The second baseline is a hybrid method abbreviated as HB. The HB method first applies ER to generate the recommendation list and user item probability matrix, which are then used as input of the GS method. First, I will present the main findings of bias reduction. We evaluate bias as the percentage of alpha similar pairs of items that violate the bit coverage parity requirement. We measure the bias reduction of 4 algorithms with various alpha values. We have the following observations. First, all 3 recommended algorithms had bias. The average coverage disparity of this algorithm is 0.1906. Second, we observe the non-negligible bias reduction by the 4 mitigation algorithms. Third, in most of the settings, ER is more effective than GS in bias reduction, while HB approach always has the largest bias reduction among all 4 methods. Then we present the results of trade-off between bias reduction and accuracy loss. We measure trade-off as bias reduction over accuracy loss and evaluate the trade-off for various alpha values. We observe that trade-off exists for all the 4 bias mitigation methods. In particular, all our methods, ER, GS, HB, have better trade-offs than the baseline MC. And in most of the settings, ER has the best trade-off among the 4 methods. To summarize, we focus on item-side individual fairness in recommender systems. First, we formalize a new notion of individual fairness named alphabet fairness. Next, we design 2 bias mitigation methods named embedding-based ranking and greedy substitution that takes different types of inputs for bias mitigation over recommendations. Third, we demonstrate the performance of both ER and GS on 2 real-world datasets and a set of state-of-art deep recommender systems. Thank you for your attention. I'm very happy to take questions.